as we're going, so feel free to ask about whatever. So today we're going to talk about named entity recognition, but before I dive into that, I thought I'd first introduce myself. So I'm a data scientist at FiscalNote, and sorry, reset the clock. FiscalNote is a company that works with a lot of legislative and regulatory data from like different countries and different US states, and we do various kinds of analysis to essentially help companies, nonprofits, and individuals better work with the government. So like one of the things I helped build was a forecasting model to help predict which bills will pass in various states and then US, and sort of how do we also make descriptions of that. Another thing I worked on was more of a traditional natural language processing or NLP task, where we try to identify key terms in a body of text. And then I also helped build a taxonomy using both handwritten methods as well as rules to build essentially a taxonomy of all policy topics. So for today's talk, we're going to have three parts. First, we're going to go through an introduction where I'll reveal what named entity recognition is. Then we're going to go over some theory and some both math and some neural networks. And finally, we're going to have a practical component where I'll actually show you some code. And I'm going to share the slides out at the end so you can have them and look at them at your own pace. So what are named entities? Well, they're really anything in the world. So let's say we have a sentence. Anastassia Kornilova gave a talk on NERs on Thursday at the WWC conference from her home in Washington, DC. So the named entities in this text would be Anastassia Kornilova, a person, Thursday a date, WWC an organization, and Washington is a place. GP is an acronym that means geopolitical entity. So really it represents anything real in the world when we want to go from text to useful things. So why might this be useful to you in like any system you're building? Well, let's say again, you have the sentence and maybe you're using an app like Siri or really any smart assistant. If you saw the name, you could offer to tag Anastassia. Or you could, for example, ask to set a reminder for Thursday. So essentially lets you pull out important things and potentially make useful recommendations for your clients. But it also just helps you organize your data. So for today's demo, I'm going to use a lot of names of female scientists because I thought it'd be appropriate. So maybe you have a lot of text data, and it might help you to know who are the actual people in the text. And if you can pull out all the entities, like people's names, you can then create a separate index. So when you want to find all the documents about Ada Lovelace, you can then know which documents you're looking at. So essentially, it's kind of like a Wikipedia index. And essentially with entities, it gives you a way to go from just free text, so like text documents, to actual kind of like objects in the world. So that's kind of what named entity recognition is. And the recognition part just means you're looking them up in the text. So how might we want to do this? Well, let's start with a simple case where maybe we already know all our entities. In that case, we could just find them using maybe regular expressions or a search type similarity method. And in my work, I have had to do this because, so one of the tasks we work on is that we get legislative data, and state governments and international governments don't have the data in a super clean format. So they'll essentially send us a text file, which represents the timeline, like what happened to legislation. Did it pass a committee? Did it go somewhere else? And what we wanted to do is essentially pull out the name of the committee they were talking about and create a link to the committee pages. So again, we wanted to go from free text to actual committee information. And so what we were able to do in this case is essentially look up like which committee was talking about by the sort of key terms in it. So while there might be the words committee in all the committees, they usually mention one specific topic. We can essentially then match which topic it's talking about. For example, education, commerce, health, technology, and then match it to a committee. So it's in a sense, it's kind of a half rule-based, half sort of statistical method that we can use. And similarly, let's say you can only tag users you know in the platform. Well, in that case, you might know that, well, there's only a few different ways that people really mention names. They might be like first name, comma, last name, or last name, comma, first name, or first initial, last name. Well, since there are a limited number of forms, you might be able to just put them all into one list and then match against all of them. So again, when you have a constrained set of things, this might be a good start because it's very clean, very organized. But there are a few limitations to it. So first of all, using something like regular expressions may be slow if you have a lot of them. You might also miss unusual variations of names, like you might not have thought of that people might refer to somebody like last name, but then the first name in parentheses. But most importantly, you cannot account for new data. So sure, you build the system at one time, you knew all the people you're going to have, but then you still need to kind of deal with cases when there's a new user or sometimes there are new committees. So you really can't deal with new data. And that is why kind of for the next portion of the talk, we're going to talk through a machine learning approach. And when I talk about machine learning, I mean, we're going to use some kind of like mathematical model to generalize over different types of examples. And in this case, I'm going to walk you kind of at a high level through like a certain type of deep learning method, but in reality, there's already lots of great libraries. So I hope from this portion, you just get a better understanding of what's going on under the hood, and also maybe get some good lessons if later you're building your own deep learning system. So that's the start. So whenever I give talks about any topic in machine learning, I like to start with the kind of equation of f of x equals y, because that's kind of what's the core of the machine learning. So in this case, x represents the properties of the text, which I'll touch on in the next slide. F is some kind of model, so it could be some kind of black box. If you're familiar with like linear regressions or random forest or neural networks, it could be all of that. And Y is going to be your prediction, which tells you, is this word a person? Is this word an organization? Is this word not an entity at all? So essentially, you start with the text, then you kind of put it through a model, and you get out a prediction. And that's essentially what supervised learning is. And then what makes it supervised is that you need a lot of labeled data. So you need a body of text where you already know who's a person, who's a not person, who's a verb, who's an organization. And the model F is learned using this labeled data. And I will talk a little bit at the end about how you can source your own labeled data if you need it. So let's make this a little more concrete. So say we want to build a per word classifier, which is essentially kind of the model we talked about. So we can maybe brainstorm some useful properties of text, like does the word start with an uppercase letter? Because a lot of entities start with an uppercase letter. What part of speech is it? For example, nouns are more likely to be entities than not. And maybe even things that aren't super obvious, like how many letters long is it? So we can take this whole like set of features we create, we can put them through the model, and that would get an output like person. And essentially, this is maybe the simplest model you can build. And that might get you part of the way, especially the uppercases might tell you a lot about what's some kind of entity, but it might still be pretty hard to distinguish between different types of entities. And this is where context can help. So FiscalNote is the company I work at, and yes, it starts with an uppercase. That's a good clue. But even more indicative is the fact that the next word here is office. And because you can sort of use the context, so you're looking back and you're looking ahead, and this might tell you that it's an organization, because organizations are often, organizations usually have offices, so context can help. So for another small example, maybe you just see the word Wednesday at first, and you're like, duh, that's a date. But then you look ahead, and you see that it actually also says the word Adams, and now you know that it is a person. So context can be really important. It can really be helpful for making better models. So that's kind of like the first section. I'm going to take a second to ask if there are any questions so far before I dive into a little more like mathy intense stuff. So take a sip of water and give y'all a second. Okay, great. So next I'm going to go through an actual method that lets you use both properties of an individual word as well as features about the context. And I'm going to go through this at a fairly high level, so don't worry if you can't follow all the math. Again, I'm really just hoping you'll take away some principles which can be helpful in other machine learning settings as well. So I mentioned that when we're doing supervised machine learning, we need to have some data. And what it will look like for us is we first start with the text or X, and we're just going to take the word. So like Marie Skłodowska-Curie discovered radium. And then we're going to assign a label to each individual word. And we're going to use this thing commonly used in natural language processing called the BLUE scheme, which is like 5 tags, and they're assigned to a separate word at once. So there's a begin tag, which means that's the start of an entity for Marie. There's an I, which represents being in the middle of an entity, in this case, Skłodowska. And there is an L, which represents being at the end of an entity, in this case, Curie. O means you're not an entity, so out. And U is radium, which means it's a single word entity. And in reality, they'd also have like a dash, which type it is. So it'd be B person, I person. And essentially, you give these two things to the model, this X and this Y, and that the model learns how to make a prediction. So I'm going to show you the diagram of what the model looks like from this paper. And you don't need to be alarmed, it has a lot of arrows. We essentially just want to go from bottom to top. So at the bottom, again, we have our input words. In the middle, we have the actual model, which in this case is something called a bi-LSTM. And the main thing to consider is there are arrows going left and right. So the different words are talking to each other. And there are also arrows coming from the bottom, which means the word is setting up information as well. And finally, at the top, we have our actual labels. So essentially, there's communication going left and right, up and down, and I'm going to bring it back to some actual equations. So in a sense, this is just a simplified view of part of that model. So at the bottom, we have the words. And instead of building up a bunch of like hand-driven features like I talked about before, like checking its parts of speech, checking for capitals, we're going to use a more abstract thing called word embeddings. There's a few common models like Word2Vec and Glove. And essentially, it's like a small representation of the word, which lets you compare it to other words. As I mentioned, a link to some Medium slides in these slides. So when you look at the slides later, you can get more information. Then in the middle, we have something called a hidden state vector, which again is a series of numbers which represents some properties of the model. And it's whatever the model wants used internally. It doesn't necessarily have human meaning. And finally, at the top, you have label predictions, which is, again, you outputting the label. So I'm going to break up that like F we talked about before into 2 parts. So first, we kind of have this internal piece where we produce the hidden vector. And that is some function which takes in the hidden state from the previous word. So again, its context, as well as information about the current word, X1, which represents that current word embedding. And then to make the prediction, we have Y1, which is just a function of that hidden state, and the model does that for each one. So the next word over, I would use hidden state 1 and make hidden state 2, and so on. And when you train the model, you essentially learn the functions F and G, and they do have like specific formulas, but it's pretty technical, and like most popular machine learning libraries already implemented it for you, so you don't need to worry about memorizing that. I certainly don't have it memorized. So that's kind of the setup, and the last piece we need to consider for now is that when I say label prediction, the model doesn't actually produce just like one label. It kind of produces a distribution of what it thinks each label could be and gives it a score. So for example, for the first word, Marie, the model thought that it's a person with 70% probability. It thought it's definitely not the middle of a person, so I person. It thought it might not be an entity at all with 10% probability. And it thought it might be just a U place with 20% probability. So this kind of scoring can be helpful, and I'll touch on that in the end. But essentially, each time we sort of produce a probability distribution. And as you see, this time it was pretty sure that it was the right thing. But maybe we're looking forward. So next word is Skłodowska, her middle name, and maybe the model isn't very good with non-English names because it was trained on a lot of English data. So in this case, we can see that the highest score was actually wrong. Like it thought it was a unit place with 50% probability. And I thought about the right answer, I person with only 40% probability. So as you can see, it's not ideal. And while there is some internal communication, it is not enough. It doesn't represent everything. And one of the limitations you can think of doing something like this is that you really can't prevent bad label sequences. Like there's some internal communication, sure, but the model might still produce a sequence like B person, I person, we can't really control. And one of the things we might want to do is incorporate an extra layer of information. So as you recall, the talk was called, had the words LSTM, CRF in it. And so far we've only covered the CRF parts, sorry, the LSTM parts. Now we're going to talk a bit about the CRF part, which stands for conditional random fields. And I'll go through a simplified version of this that kind of gets to the core ideas. So again, we have a bunch of labeled data, and we might know what, like, we can look at all the tags in the labeled data and use some information about them. So for example, we can count all the real tags, and we might see that B person is followed by I person 40% of the time, which might represent that 40% of the time you have a middle name, 60% of the time you go straight to L person. So like, you know, it represents a balance. But then the next line represents something that can never happen, going from inside an org to L person, which is why that has a 0% kind of chance of happening. In the next session, you have that unit org goes to 0, O, always, because a single word entity must always be followed by not an entity. And second, going from a non-entity to a non-entity might have 80% probability just because there's a bunch of words that aren't entities. So let's say we can calculate this table, which gives us a bunch of useful information. And now we're going to add it to the model. And this is going to be in form of this transition score, which I showed in the table on the previous page. So now we'll want our model to, before it makes a prediction, to look both at this score, as well as that initial hidden word score. So what might this mean? So again, we have a table, and that first table represents the distribution we had before. The second table represents that transition probability. And so here we had the green parts, we had uPlace at 0.5, and uPlace must be preceded by an O tag because it's an individual word. So we have 0.5 plus 0.2, which gives us 0.7 or a 70% chance. But now we want to consider a new possibility. And in this case, we'd have I person, which is at 40%, but going from B person to I person is also at 0.4, which means that the probability of this new sequence shown in pink is actually higher. And so the next thing to remember is that we're not looking at this one step at a time. We're kind of trying to label the whole sequence at once, which means we would have also considered the probability of the first word being B person. So essentially we add up all the pink scores and we add up all the green scores. And the model is able to combine both of these sources at the same time. And the specific labeling is done with an algorithm called forward-backward. Again, there's lots of materials on that online. So this is kind of the first part. So what am I hoping you will take away from this part of the talk? Well, first of all, I'd say that context is important. We've had kind of a couple of examples about that, but essentially if you can incorporate context when you're working with text, it can help a lot. Next, when you're building some kind of machine learning models, you might want to consider several different sources of information, like both the individual word score and the previous tag. And finally, no matter what you're doing with machine learning, I'd always keep in mind your human knowledge. For example, you might want to check even by hand that you'll never produce illegal transitions. Like I often worked with systems where we started with a machine learning model, but then we added some rules to make sure like the model didn't do anything super crazy. So that's kind of this theory portion of the talk. Again, I'll give you guys a couple of seconds if you have any questions before I move on to the more practical portion of the talk. Okay, great. No questions for now. I mean, don't be shy, but so you're like, well, this is great and all, or you might be thinking, this is all super confusing. What is this girl talking about? But let's think about what we can. Okay, sorry. Are there other sources of information you could add? Well, yeah, for example, you might have lists of known entities. Like there's lots of lists of like known organizations, and you can essentially have an ensemble where you consider those two scores, but you also consider, does this word appear in a known list? Like the way we had a formula which combined two things, you could essentially extend the formula to combine as many different things as you want. It's really flexible. You can just like make up the score whatever you want it to be because it's kind of arbitrary. So I hope that makes sense. Yeah, so I have a logo for SpaCy up, and SpaCy here is like my favorite thing. It's a natural language processing library in Python, which works really well, and it lets you both know the named entities in your text and also other useful features, like it will break up your text into words and tell you also how the different words are connected to each other. So very useful. I use it all the time, and I'm going to kind of walk through how to use it. Even though they do have great tutorials, I just thought I'd get you started on it. So remember the example I showed you in the beginning? Well, this was actually produced with SpaCy with no additional training or anything. So always start with existing solutions. Like, if you have some text coming in from your users and you want to see it, like just run some examples for the data. And for this one, they actually have an online demo you can look at and mess around with. So again, start with existing solutions. They might be good enough for you. And to show you what that would look like in your code, it's literally just a few lines. So this is Python code. We first import this library, which you can download with pip or conda. Then we have the model. So SpaCy has a bunch of pre-trained models, which means they took all the stuff we talked about and they had a whole ton of labeled data, and they were able to already train a model for you. They don't use quite the thing I showed you on the previous page, but they use something more complex, but still basic principle. So here, the first part, EN, means it was trained on English. They have about, I think, 15 or 16 other languages. The middle part, core web, means it was trained on a bunch of data from the internet. So it includes Wikipedia, as well as a bunch of other sources. And the SM part at the end means it's small. So some of those internal vectors, they're relatively small, which means that it takes up less space in memory. And depending on your application, especially if you want to load it in like a small machine, that usually might be good enough. In the next line, we have just the text, which is a regular Python string. Then we kind of do this magic where we apply this NLP class to the text. We get out a doc, which is essentially a class which represents all the linguistic and syntactic information about this word. And finally, the named entities are stored under doc.ents, and it's an iterator. So you can go through them. And in this case, it produces the output Lisa Maitner, and the label is person. So that's it. That's all it takes. And yeah. So to kind of set the context, this magic NLP thing, it actually does a few things. It's a pipeline, which starts with the text, then it applies a tokenizer, which means that it splits it up into actual words, because you just have a string on your computer. It doesn't really mean anything to the computer. Then it applies a tagger and parser, which labels the thing with parts of speech and also dependencies between the words. And then finally, it has the NER layer, which goes through all of that and applies those named entities. And you can add other things to it, but essentially it comes up with the doc class at the end. So essentially it does all this for you. It's pretty straightforward, but in the real world, when you go to do something, it obviously won't work so well. So I was messing around with the demo, for example, and actually for some reason in another, I'm going to touch on the data samples thing in a second, but that's a great question. So for example, it thought my name was an organization when I typed in just my name. I don't know why. And it also thought my position title was an organization as well. So this is kind of like two types of error at once. One of them, it labels something as the wrong type. And in another one of them, it labels something that's not an org as an org. And in the second line, it misses two names, Anna and Kat are scientists. So this kind of shows you different types of errors, and depending on your application, for example, are you showing this to your user? Are you just kind of using it to collect potential entities that you might index? You have to think about what sort of things are important. And unfortunately, you can't do this with SpaCy directly, but one thing to think about is, again, that label distribution we talked about before. So for example, if you want to be really careful and label everything, and in this case, let's say we build that model from the previous section, but it labeled research scientist with only a 60% probability. If you really wanted to capture every possible entity just in case, you might think this was okay. On the other hand, the reason you might not have labeled cat is because it had 60% probability. So in this case, you kind of have to decide what you want to do. And maybe if you need more precision, you only label something with a 90% probability. So again, you have to kind of think about what you're going to use your data for. For example, in one problem I worked on, we kind of initially pulled everything out, but then we used some procedures on top of it to only show a few things. So to talk about the actual data, And I'm going to address your question, Carol, in a second. Sometimes the initial SpaCy model isn't really all that good. And essentially, I had to actually deal with this like a couple months ago. We were building a feature where we wanted to tag people that were mentioned in the user's platform notes. And because people would like paste in emails or just use shorthand that didn't really look like the Wikipedia text, it wasn't working that great. So one thing you could do is you could take a whole bunch of text and you could sit and label it by hand. That's pretty tedious because, as you recall, you have to label every single word, but you could get really sharp results. Or another thing you can do is you can start with a known list of entities. So for example, for us, we knew that a lot of people in our system were talking about legislators. So we used some stuff kind of like the regex I talked about in the first part, and we labeled the data with them, even though we knew it wouldn't be perfect. And for these types of things, I'd actually say like even like a couple thousand examples might be enough. Like SpaCy's website has a few toy examples where they just did a few hundred. It really depends on like how different your data is from like the original model you have. So I'd say 10 examples is definitely not enough, but you might be able to get away with just a few hundred. It really just depends on your data, but I'd say for some things, the few hundred is enough. So as I said, you might start with a known list. So maybe you do like partial labeling where you use some regexes. Maybe you label a bunch of things by hand because you want to be really careful. When you do all that, SpaCy actually has a really easy command line interface to help you run the model. I'll just go for this really quickly. It looks like this. You'd run this on your like bash command line. So the first part of this command, because it can be a bit confusing, just tells you we're going to train the model. The next part talks about what language it's going to be in, so English for us. The next part you type in is just where do you want to store the model? And the next part you'd have the data. And SpaCy has a very specific format for the data, which is a little tedious to use, but they have some details around that. And again, it sort of points to why it's kind of hard to label everything by hand. And finally, you have a base model. And you usually want to start with like a basic model because it already knows a ton of great info. So it already knows a lot about English. You just want to tell it a little more about how people actually type their own notes in. And let's say you do this, and let's say you kind of only partially label the data. So you use something like that entity ruler, but you kind of knew it was missing some things. Maybe it gets really high accuracy, but you're not really done because we only knew about some of the possible people. Now let's say in their real world notes, they also had various contexts or weirdly spelled names, or maybe you're looking again at your female scientists and you start with a list of historic scientists, but there's always new up and coming scientists. So maybe your training data actually had the issue where you had Marie Curie, a known one, had dinner with Katie Bauman, the woman who took the picture of the first black hole this year. And because she wasn't in your historic known list, you won't know about it. So even though your data looked like you had 100% accuracy, that might have been wrong. And something you can do for this is a technique called active learning, which I had to use for my application, where essentially you start with your just kind of okay data, and then you put it for the model. And because the model is smart and it saw a bunch of other people labeled correctly, the model might disagree with you and be like, actually, I think it's this. And it would literally give you back that result. And then you as a person can decide if you can assign a better label, and then you can put that through the model. So this is actually a human in the loop approach. There's a paid version of SpaCy, they have a separate package called Prodigy, which literally gives you the UI. But the idea here is that you can use a lot of tricks so you don't have to sit and label 10,000 examples by hand. The idea is you started with some known list of people, you labeled them, you trained the model a little, you saw where the model disagreed with you, you clean up those confusing examples, then you train again and go on. So there's lots of useful stuff, and there's lots of great SpaCy documentation around this. Kind of a big SpaCy fangirl, but this is the idea. So what I'd hope you take away from the second part is, first of all, you always want to test some existing solutions first, because for a lot of things, they might be good enough. Next, you should understand, when you're working with named entities, what do good results look like for you? So again, we were getting a lot of false names when we were trying to pull names out of people's kind of user nodes. But then we had a separate algorithm to match them to actual people in our system, which helped us with precision. So There's no right answer. You have to know what your application looks like. And finally, I'd always say, don't just trust your metrics. Like, as I briefly alluded to, 100% accuracy isn't always good. So always actually look at your data. And I hope some of these things will apply beyond just named entity recognition. I think there are a lot of general good machine learning data science principles in this. So that's the talk. You can find the slides there, and feel free to email me. I love to answer any questions about your life in data science or whatever else. And that's that. So I guess we have a little bit of time for questions. Just gonna take a sip of water first. Yeah, so
Anastassia, that's fantastic.
Yeah, so for the data that you used for training, let me go Emiko's question. Yes, so essentially you essentially have your own data and you just label like a few hundred examples of your own, but you essentially assume SpaCy's models that you literally download were already trained in a bunch of data. So yeah, you just label some additional features. So let me see the next question. Where word meanings not have changed over time, though. Do you have any thoughts on
read it out?
Sorry, I read out loud when I read to myself.
I can read it out for you.
Yeah, sure.
Pamela said, thanks, Anastassia, great overview. I work with large historical to extent corpuses, I think 1600s to present, where word meanings not to mention spellings. I have changed over time, though we also see these changes on shorter time periods too. Do you have thoughts on libraries or approaches to check out that could accommodate the necessary flexibility for that added complexity?
Yeah, so I have a couple of thoughts. So first of all, like you could start with like the current model that in English and use something like that live training approach I talked about, where essentially you kind of expose the model over time to some more historic data. And in fact, actually, no. So you could do that. Or there's some stuff around how I think there are parallel corpuses which have kind of like old data and new data in some parts of the NLP world. So if you want, you could almost run like a machine learning model to translate from older English to newer English. But those are just things that come up off the top of my head. I'm not as familiar with working with historic data, but I'd say you might want to label some historic examples by hand and hope your model gets better over time, or maybe look at it, you can almost like machine translate from older English to newer English, but I admit that's harder.
Elvita just said, I learned so much. Thanks, Anastassia.
You're welcome. I'll give you a couple of more minutes for questions. I can still stay on for a little bit, so if there's any last minute ones. And again, feel free to email me if you come up with some later.
Yeah, if anyone just has any questions, please pop them into the chat here at the right-hand side. Mela said, thank you. Was hoping there'd be a less time-intensive manual step than the more labeling and training.
So actually, I forgot one thing. So the way SpaCy works is that it has like an underlying component which is just a language model, which means that you don't have to label it. It just tries to predict kind of the next word in the sentence. So it kind of learns on its own. So it's called, I think, the fine-tune operation. And for that, you could essentially run it through the fine-tune step. So you just show it your historic text and you run it through the fine-tune step. And then you do have to label some data, but probably less data. So that could work. Let me see if I can pull it up really quickly, if I remember where it is. But essentially, yes, usually it has a general underlying step. So yes, but yes, unfortunately, this is just the SpaCy website. It's spacy.io. So yes, it's actually called pre-train, and it's a little more experimental, but if you look into it, you could run just a bunch of historic unlabeled data through it, and that might work. But again, not my total area of expertise, unfortunately. Yes, labeling data is hard, I understand. So let's see, is there sorry, I'll pull the screen back up.
Yeah. Tara just said, I'm considering getting into data science as it's related to what I do now. is there particular training or skill that you would recommend? And Tara already has a master's degree, so she's not sure she wants to go back to school full time.
Yeah, so I kind of am lucky. Like I learned most of what I know on the job because I kind of got lucky to get that opportunity. So one of the things is like just find a side project and start working on it. But I have heard pretty good things about the METIS, METIS bootcamp, as well as about General Assembly. But I'd say even if you do those, like they might be relevant for a bit, but I'm constantly exploring new libraries all the time. So data science is kind of the sort of thing that you kind of have to learn for yourself, for better or for worse. And like if you work for like a supportive company, they will invest in your growth because they realize the industry is changing as well.
I totally agree with you there. It's always changing, and there's just so much happening at the moment. I was actually investigating SpaCy in my previous project, and also one of AWS's technologies, Textract.
Oh. Yeah, I haven't worked with that one, but I think actually some people like on another team have used it. If you're talking about the OCR one, but yes, like luckily these days the tools have like really nice interfaces. I remember it not being that way like 5 years ago, where you had to like use these like horrible academic research codes that might not compile. So really in the last like 2 to 3 years, it's gotten like so much easier to work with. So
yeah. Oh, it has. We have a few, like Anya said, seeing the article was incredibly helpful, and it's comforting to know that we're not alone. And
I wrote a blog post about anxiety a couple of weeks back, and yes, thank you. Anya's actually my friend, so thanks for the pep talk, girl. So yeah, well, again, as I said, like I know we have to wrap up this session, but feel free to email me, and really happy to talk about this sort of stuff and machine learning in general as well. Yeah.
Yeah, thank you so much, Anastassia. It was a fantastic talk, and I definitely learned a lot from it as well. Just to let everyone know, this talk will be recorded and published onto YouTube as well, so we can share it afterwards too. We will be sharing it on the Women in Code Data Science Slack, and it's going to be on the Women in Code YouTube channel as well.
Yeah.
It was a very informative talk, but again, we have like 1 minute left if anyone wants to ask any more questions or reach out.
I am going to be so we don't have it set up yet, but if you can find the DC chapter, I am going to be doing kind of a more practical Python lab about actually coding with SpaCy. So it's going to be streamed through Twitch since we're all virtual. So if you can remember to look that up, that's going to be happening. But we haven't set up the meetup event yet. That's why I couldn't share the slide. But
yeah,
moved along in a couple of weeks. So if you can remember or like figure out a way to find it, that's also happening.
Yeah, we can share that also in our Women in Code Data Science Slack as well. So we'll definitely keep an eye out, and then we'll publish it there too.
Yeah.
Just to remind everyone as well.
No, our Python lead should be making the event in a day or two. She just hasn't had the time yet. So
awesome. Cool. I'm looking forward to it.
Yeah.
You got very positive feedback. Everyone's saying thank you. They'll look at Pamela wants to look more into SpaCy and play around with it.
Great.
And said, thank you, such a clear and interesting talk. Elaine said, thank you so much for your talk, Anastassia. And Carl said, thank you so much. I enjoyed the talk. So thank you, everyone, for joining. And a big thank you again, Anastassia.
Well, I'm glad you all enjoyed it. It really means a lot to me. And yeah, well, have a nice rest of your day or evening or morning. I know we're like really spread out. So
thank you. Bye, everyone.
Bye.